3.6 is about the chain rule, and the chain rule can be one of the toughest derivative rules to recognize in calculus. And what the chain rule does is it tells you how to take the derivative of a function that's really the composition of two functions. For example, h of x is f of g of x. It's where you take one function and stick it inside another. So the chain rule, there are two versions in the book. I don't care what version you use. When I talk about the chain rule, I talk about drawing boxes to help you identify the g of x. But when you do the practice problems, you can do them in any way that you want. My only desire is that you get the right answer in the end. So I don't care which version you use or which method to understand it works. It's just whatever works, that's the one you should use. This is the chain rule that's the easiest to illustrate what I'm going to show you. H of x is a composition f of g of x. Then the derivative of h of x is f prime of g of x times g prime of x. And that's confusing. It doesn't really mean anything unless you really understand it, so it doesn't help when you're first learning it. But the idea of doing the chain rule, at least one method to do it, is to draw a box around g of x. And now that begs the question, how do I find g of x? Well, usually you find g of x in parentheses, or they're the arguments of trig functions, like the sine of 5x. Or they're the arguments of log functions, like the natural log of 8x squared. 8x squared would be the argument. You also find g of x in powers as well. So parentheses and in powers and as arguments of like existential functions, like or transcendental functions, like log and sine and cosine. So to use the chain rule, you draw a box around g of x, wherever you find it, and then you take the derivative around the box. That means whatever's inside the box you leave alone. And it's just the stuff on the outside of the box you take the derivative of. You treat the box as a big old x. This is the f prime of g of x. This is that first factor when you look up here. F prime of g of x, that one is the derivative around the box. And then you take the derivative of what's inside the box. That's the g prime of x in the chain rule there. And then you multiply those two things together. The derivative around the box, which is step 2, times the derivative inside the box, which is step 3. So once you get good at drawing boxes around g of x, then you take the derivative around it and inside it. And the chain rule's not so daunting. But you have to get used to it. Eventually you don't have to draw the boxes. So let's just look at an example. For example, h of x is 3x squared minus 4x all to the second power. And just to note, this really is the composition of two functions. If f of x is x squared and g of x is 3x squared minus 4x, then f of g of x would give me the function h. That is the composition of these two functions. And again, you want to draw a box around g of x, and you can see that in this case g of x is in parentheses. A lot of times g of x will be in parentheses, or it will be in powers. So if I want to find the derivative of this thing, I have to take the derivative around the box. That means I leave the box alone. I'm not going to change anything inside this box, because this is around the box. And to take the derivative around the box, I treat it like a big old x. If you can think of this box as an x squared. The 2 comes in front. The 2 here will come in front. And it'll go to x to the first power. That's the derivative around the box, which represents the f prime of g of x. And then I multiply it by the derivative of what's inside the box. The derivative of 3x squared is 6x. The derivative of 4x is 4. So the answer is 2 times 3x squared minus 4x times 6x minus 4. And you don't have to go any further than that. You can leave your derivative just like that. Now if you wanted to expand it out, this is 6x squared minus 8x plus 6x minus 4. This is just so I can compare doing it, just so I can write it a different way. And if you multiply this out, you get 36x cubed minus 24x squared minus 48x squared plus 32x. And so you get 36x cubed. 24 and 48 is 72. x squared. You could also expand it all out if you wanted to, but both of these are correct answers for the derivative. So note, once you identify g of x, you put it in a box, and you take the derivative around that box times the derivative inside it. Now let's try it again, this time with a square root. Here I have the square root of 2x to the fourth minus 7. It may not look like g of x is in parentheses, but if you rewrite this as a power, this can be written as 2x to the fourth minus 7. The square root is the 1/2 power. As soon as you rewrite this thing as a power, the parentheses are now visible. And that's a good idea with square roots, is to write the roots as powers, so it's easier to see the parentheses. So now to find the derivative, I figured out where my box goes. And to take the derivative around the box, the stuff inside gets left alone. 2x to the fourth minus 7. I don't touch it. To take the derivative around the box, the 1/2 comes out front. And when I take 1 away from 1/2, I get negative 1/2. That's the derivative around the box. Now I multiply by the derivative of what's inside the box. The derivative of 2x to the fourth is 8x cubed. The derivative of negative 7 goes to 0. So I can simplify this. Notice the 2 cancels the 8 and leaves me with 4. And so on the top I have 4x cubed. Since the 1/2 is the square root and it's negative, the square root will show up on the bottom of the function because it's a negative 1/2. So that would be the best way to write the derivative. But this is around the box and this is inside the box. And then you simplify. So once you pick off g of x, that's really the harder part of this thing. Let's look at another. 5x squared plus 11x to the 20th. That's a composition of two functions. X to the 20th would be f. 5x squared plus 11x would be g. But you can see g because you have the parentheses to tip you off. So to find the derivative, I take the derivative around the box. So I'm going to leave what's inside the box alone. The 20 comes out front. It goes to the 19th power. That's outside the box. Times the derivative inside the box is 10x plus 11. There's not a lot you can do to simplify. I could multiply the 20 to the 10x plus 11. I get 200x plus 220 times 5x squared plus 11x to the 19th. I just multiplied that 20 through. Yet another example of the chain rule. Here we have the sine of 3x squared. The arguments of trig functions are the g of x is a lot of times. F of x is the sine of x. G of x is 3x squared. So now I'm going to take the derivative around the box. Now this can feel a little weird because we have a trig function on the outside. But when I take the derivative around the box, I have to leave the box alone. So I leave the 3x squared alone. Now if we think about it, the derivative of sine is cosine. So when I take the derivative around the box, I take the derivative of sine, and I get a cosine of 3x squared. This is a round box, or outside the box. Then I multiply by the derivative inside the box, which is 6x. So I get 6x cosine of 3x squared. So notice the trig function is what changes when I take the derivative around the box. Here's another one. X squared times the secant of 5x. This is a product rule. First and foremost, notice I'm multiplying two functions of x. My first one, which I'll call u, is x squared. My second one, which I'll call v, is the secant of 5x. Now the derivative of x squared is 2x. It's just a regular polynomial. But to find the derivative of the secant of 5x, I have to draw a box and use the chain rule, because I have something inside there that's not just an x. So the derivative around the box would be the derivative of the secant. And the derivative of secant is secant tangent. So I'm going to leave the box alone, but when I take the derivative around the box, I get secant tangent. So that's secant of the box, tangent of the box. Notice I don't change the box when I take the derivative around the box. So I get secant 5x, tangent 5x. This is a round box. Now I have to multiply that by the derivative inside the box. The derivative of 5x is just 5. So I get that my derivative for v prime is 5 secant 5x tangent 5x. And so now I can use the product rule. The product rule says that it's u v prime. U is x squared. V prime is 5 secant 5x tangent 5x. So there's uv prime, 5x squared secant 5x tangent 5x, plus vu prime, which is 2x secant 5x. So notice I used the product rule to find this derivative, but one of the terms in the product rule required me to use the chain rule. So uv prime is 5x squared secant 5x tangent 5x, plus vu prime is 2x secant of 5x. So again, with these chain rules, especially with trig functions, it gets a little bit weird. So let me look at a couple more of these. There are three left, but this one here is notorious, the cosine squared of x. It's hard to see any parentheses here until you go and rewrite it as what it really is. The cosine squared of x is really the cosine of x all being squared. So if I rewrite it this way, and that's the trick with these trig functions, that's really what it means, then it's easy to see where the box goes. The box goes around the parentheses. And so I have to take the derivative around the box times the derivative inside the box. Well, the derivative around the box means I leave cosine of x alone. So the derivative around the box means I leave cosine of x alone inside. The 2 multiplies out front. It goes to the first power. Inside the box is the derivative of the cosine of x. And the derivative of cosine is negative sine. So this is negative 2 cosine x sine x. A lot of times people don't recognize that this is a chain rule, especially when it's written that way. But if you rewrite it in the correct form, it's easier to see how the power comes down. So that's a good one to look at. Notoriously shows up on tests and causes issues for folks. Here's another one, e to the 3x to the 7th. Remember, when you take the derivative of e, you get back what you started with. And then for a little while, they showed you another trick, in the powers, and didn't explain it. But that trick really was the chain rule. When we look at e to a power, sometimes our g of x is in the power of a function. We know the derivative of e to the x is e to the x. But now I have other junk up there in the power. So when I find the derivative of this function, the box, in this case, is going to be in the power of e. And when I take the derivative around the box, I leave that alone, what's inside. Well, the derivative of e to a power is e to that power. So I get e to the 3x to the 7th. But then I have to multiply by the derivative inside the box, which is 21x to the 6th. So this is 21x to the 6th, e 3x to the 7th. When taking the derivative of an e, you get back what you started with times the derivative of the power. So I get e 3x to the 7th back times the derivative of 3x to the 7th, which is 21x to the 6th. So with e, you get your function back times the derivative of the power. Well, let's look at the last chain rule example. It's a nested chain rule. But to see how this works, I'm going to write it as powers. So I have the square root of x as x to the 1/2 power. And since there's a big square root around everything, there's a 1/2 power around the outer parentheses. So notice I have the square root, that's the big one, the 1/2 on the outside, x plus the square root of x, which is the little 1/2. So if I want to find the derivative, I need the chain rule, which means I need to draw a box around the parentheses. So the derivative of this, I have to take the derivative around the box, which means I leave all the junk inside the parentheses alone. Notice a lot of times writing things as powers makes the chain rule, and derivatives in general, easier to work with. The 1/2 comes in front. 1/2 minus 1 is negative 1/2. That's the derivative around the box. Now I have to multiply by the derivative inside the box. The derivative of x is 1. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. That's inside the box. This is most of the work. If you got to this point on a test, you would get most of the points for the problem. But I'm going to make it look nicer by simplifying. Or at least I'm going to write it a little differently so it doesn't look so all over the place. That's the negative 1/2, so it's the square root on the bottom. And this is 1 plus 1 over 2 square root of x. So it just looks a little nicer when I write it this way because I put the square roots back in since they were in my original problem. Notice x to the 1/2 is the square root of x. Since the whole thing was to the negative 1/2, then the whole thing is on the bottom of the square root. The 2 is on the bottom of the fraction as well. X to the negative 1/2 means it's the square root down by the 2.